This is Clearance, an air traffic control simulator that I built on Unreal Engine 5, targeted at defense-relevant modeling and simulation. There's a video on the DIS DDS RTI and HLA Federation layer, and a video on the two Simulink subsystems that fly the aircraft and detect them on the radar. This video is about the layer underneath both of those, the C++ engine that owns the simulation, and everything that's being built on top of it. The sensor fusion, the electronic warfare, the networked instructor station, the session replay, the checkpoint workflow, the after-action reporting, the voice input and voice output, the phraseology parsing, all the automation test suite, and the whole thing wrapped in a VR operator station on a public geospatial reconstruction of the Wharton airfield. One thing that is worth saying before this deep dive is that Clearance didn't start this wide. The original plan was a focused air traffic controller training simulator, the aircraft movement, the voice instructions, the conflict detection, and the scoring and replay. As the project developed, each extension came from a specific simulation problem rather than feature creep. This came first because I wanted the sim state visible on the defense style wire. However, after DSET 2026 at Cheltenham, interoperability became a bigger focus. So DDS, RTI Connect, and HLA were all added as separate federation models. The aircraft behavior started as analytic C++ movement. Then, Simulink-generated autopilot code was added to explore model-based integration. And the radar started as an analytic detection model, then expanded into a Simulink DSP chain with generated C. This architecture isn't everything bolted on randomly. It's the result of the project moving from an air traffic controller prototype into a small synthetic training ecosystem. The entire simulation lives in one Unreal Engine plugin, Clearance Sim. 9 subfolders: airspace, aircraft, comms, safety, scenario, scoring, simulation, UI, and the core. All split by systems, and not by class. No cross-folder dependencies except through the core header. If a class needs to reach across a boundary, it goes through a delegate or blueprint callable getter, and never a direct include. Core holds the shared types: the aircraft state struct, the instruction struct, the conflict event struct, the incident record, every enum, every delegate signature, every tuning constant, wake matrix distances, TCAS thresholds, vertical minimas, service ceilings, and every other folder includes this and only this from the shared side. It's the contract between the systems. Then, 2 more plugin modules alongside the main one. Clearance Autopilot MBD wraps the generated C from the Simulink Autopilot, and Clearance Radar MBD wraps the generated C from the Simulink Radar Signal Processor. Both of these are covered in the Simulink video, and both auto-detected by their build CS at compile time. If the generated C is present in third party, a preprocessor gate flips and the wrappers switch from stubs to the real code. If not, the wrappers no up and the sim runs on their fallback. And that's pretty much the whole model-based design integration scene. The first and arguably most important architectural principle is a single source of truth. Every aircraft in a simulation, its call sign, the position, the altitude, the speed, its heading, the phase, the wake category, the threat class, its jamming state, the emergency state, the service ceiling, the operating envelope, are all owned by one class, AClearanceAirspaceManager. Nothing else in the simulation stores a second copy. Every read goes through a getter, every write goes through a controlled request path. The map itself is private. And for the map itself, 2 entry points mutate this map: the registration, when the spawn or federated pair adds an aircraft, and request state update, which is called from exactly one place, the aircraft's behavior object, at the end of its per tick step, and that's it. No other class can write to the aircraft state. If it moves, if it changes altitude, if its phase transitions, it went through this one function. And now, heading to the second architectural principle, a single movement executor. Every aircraft has one instance of this per call sign. It's a UObject and not an A actor, because it doesn't need any real world presence or collision. It just needs a tick call from the controller. And this class is the only thing that actually permits an aircraft to move in the simulation. And inside, I have the gradual motion under simplified flight dynamics constrained by aircraft performance limits. The turn rate is limited by bank angle. The bank angle is limited by aircraft performance category. The climb rate is limited by category and altitude density. The speed envelope is clamped against the minimum and maximum operating speeds. The wind drift is applied to the ground track, and every aircraft goes through this on every tick. Or, if the aircraft is under the Simulink autopilot, the same wrapper hands off to the generated C. The interface stays identical. Aircraft stay in, and updated aircraft stay out. And now, the third architectural principle, the read-only safety analysis. The conflict detector does not own any aircraft state, it doesn't mutate anything, it reads a snapshot from the AirSpaceManager, runs 3 concurrent analysis, and broadcasts events. The distance separation against ICAO thresholds, the trajectory projection to catch impending losses of separation before they happen, and wake turbulence separation using the ICAO DOC 4444 category pair matrix. Advisory at 8 nautical miles, warning at 5, critical at 3, vertical minimum 1000 feet, wake separation ranging from 3 to 6 nautical miles depending on the follower and leader's wake category. When any of these thresholds trip, a conflict event fires. Response, a go around, a scoring log entry, an operator advisory happens entirely elsewhere. This class only detects, it doesn't react. And now, the fourth architectural principle, validation before any execution. Every instruction the operator issues, whether that's voiced out or typed out, is checked by this stateless validator against the current aircraft state before it's ever allowed to reach the behavior object. Heading validity, altitude within service ceiling, speed within operating envelope, bank angle feasibility for the requested turn rate, approach geometry feasibility relative to the active runway, wake separation feasibility on final approach against the aircraft in front. If any of these checks fail, the router rejects the instruction within a reason and the operator hears a negative readback. If everything passes, the router hands it to the behavior object. And now the comms router, which is the seam. It receives instructions from the parser, which itself receives from voice input or the type console. Runs the validator, routes valid instructions to the appropriate behavior object, enforces a minimum interval between instructions on the same aircraft, so an operator can't spam inputs. Broadcasts the result event for the transcript and the UI. It never mutates aircraft state directly, it's a strict middleman with rules. The controller runs the entire show. Every actor in the simulation takes in a specific order every frame. This is where the determinism lives. 9 steps in an entirely fixed order. 1. The spawner checks whether a new aircraft should enter the sector, based on the current spawn interval and difficulty. 2. Behavior object step. Each one reads its state, applies its pending instruction, computes new position with wind and flight dynamics, commits back to the AirSpaceManager. 3. The conflict detector runs on committed snapshot, distance, trajectories, and wake. 4. Go-around triggers and advisories are routed through the comms router. 5. Scoring consumes conflict events and phase transitions, logs incidents, updates the running score. 6. Difficulty adjustment is checked and broadcast. Spawn rate scales up or down against the operator performance. 7. Radar sites paint their tracks against the current airspace, applying jamming and chaff effects per site. 8. The instructor station's replicated state is written. The aircraft rows, the scoring log, the operator tracks, the notifications are all committed to the replicated properties. 9. Delegates broadcast the change. Unrep fires on clients, and the blueprint listeners get notified. The UI redraws. The order is fixed and truly matters. The behavior has to run before conflict, because conflict analyzes the committed state. Conflict has to run before scoring, because scoring logs conflict events. And the radar has to run after airspace commits, because radar reads the fresh aircraft positions. If any step slips, later systems read stale data, so the controller owns the ordering, not each individual class. There are only 3 actor-tick participants in the whole simulation: the controller, the AirSpaceManager, and the spawner. Everything else is a UObject called by the controller in dependency order. No system independently drives its own tick, no hidden ordering surprises, and no race conditions. The systems communicate through delegates, and not through direct calls. The AirSpaceManager broadcasts registered, deregistered, stay updated, and runway changed. The conflict detector broadcasts conflict detected, conflict resolved, go around required, wake turbulence advisory. The comms router broadcasts instruction result and advisory warnings. The scoring system broadcasts score, updated and difficulty adjusted. And this is what makes everything on top of the core compose cleanly. The DIS emitter subscribes to state updated, the DDS emitter subscribes to state updated, the scoring log subscribes to conflict detected, the after action review export subscribes to score updated, the transcript pipeline subscribes to instruction result, the instructor station's operator scope subscribes to state updated. Every feature added later on is a subscriber to the same events as the local simulation. There's no parallel plumbing per feature. And now, the strict presentation boundary. Every line of simulation logic is in C++. Every line of blueprint is presentation. There is no simulation state stored in any blueprint, and there is no simulation logic in any blueprint. Blueprint reads from C++ through blueprint callable getters, and takes input from the player through server RPCs on the operator's player controller. The panel base class exposes a getter for every piece of information the UMG side needs. Aircraft rows for the sidebar, the scoring log for the performance tab, the transcript entries for the comms log, the radar tracks for the operator scope, the waypoints and runways and airway segments for the sector chart, the emergency entries with countdowns, the camera overlay lines, the manual sections. Everything that the blueprint renders comes right through here. The blueprint never sets its simulation state. If you deleted every blueprint in the project, the simulation would run correctly with no UI. If you deleted a system in C++, the widget would just show blanks. So if I open up the widget blueprint instructor panel, you can see that this means that the UI can be redesigned or reskinned without touching a line of simulation code, and it means that the same simulation can drive multiple UIs. The instructor station on a flat monitor, the operator VR scope on a diegetic monitor inside the tower, the after action review replay viewer, and a headless dedicated server for network federation. The same C++ engine underneath every single one. The runtime layer. This is the sector, live. Every aircraft you see on this scope is a call sign in the AirSpaceManager's map. Every time one enters the sector ring, the spawner calls register aircraft with a spawn data struct, call sign, entry position, altitude, speed, heading, initial phase, the wake category, the performance envelope, and the threat class. The manager creates a state entry and broadcasts on aircraft registered. The controller catches that event, creates a per aircraft behavior object, and drops it into a tmap fname UClearanceAirspaceManager. That's the entire lifecycle setup for a single aircraft. The data block that you see next to each symbol, the call sign, the flight level, the ground speed, the heading, is all drawn by the instructor panel by reading get aircraft rows off the controller. Every field in the block traces back to a getter on the AirSpaceManager, which then traces back to the state committed by the aircraft's behavior object at the end of the last tick, and that's the whole read path. The AirSpaceManager also owns the sector environment, the wind direction, the wind speed, the available runways, the active runway, all computed from wind direction, updated dynamically. When the wind shifts past the threshold, the active runway swaps. An on-runway changed event fires, the camera overlay updates, the runway designator flips amber on the newly active end, and any aircraft on approach have their approach geometry revalidated, all from one single event. The flight dynamics. Every aircraft has a performance category: light, medium, heavy, and super, driving as physics envelope. The bank angle limits per category, the service ceiling per category, the max climb rate per category, the minimum and maximum operating speed per aircraft type, all enforced during instruction execution. The wind drift is applied to ground track every tick. Density adjusted climb rate accounts for reduced engine efficiency at altitude. An ISA lookup table maps altitude to atmospheric density and scales climb performance. That's why an aircraft cleared to flight level 300 climbs faster in the first 10,000 feet than the last 10,000. Each aircraft goes through phases: en route, approach, landing, go around, departing, exiting. Phase transitions fly off approach clearances, off landing threshold crossings, off exit ring crossings, off conflict triggered go arounds. The scoring system consumes phase transitions to log successful landings, successful handoffs, unresolved exits, and missed handoffs. When the Simulink autopilot is engaged, which is by default on for every aircraft. This same behavior object hands off to the generated C. The wrapper computes outer loop targets in C++, pushes them into the model's input struct, calls autopilot step, reads the control surface commands back out, applies them to the aircraft's dynamic as bank rate, climb rate, and throttle. The same commit path back to the AirSpaceManager. The rest of the sim does not know or care whether the analytical path or the Simulink path drove the update. And console vector command. Same path as a voice instruction. Parser to comms router to validator to behavior to autopilot to airspace commit. Aircraft banks, turns, rolls out on 90 under Simulink autopilot control. Instruction validator, stateless. Every rule is a pure function of the current aircraft state and the proposed instruction. Service ceiling check on altitude. You can never clear 737 to flight level 500. Minimum operating speed check, you can't slow it below stall. The maximum operating speed check, you can't push it past its VMO. The bank angle feasibility on heading changes. The turn rate implied by the requested heading over the pilot's expected compliance time has to be inside the category's bank limit. The wake separation feasibility on approach clearance, you can't clear a light aircraft in behind a heavy inside the wake minimum. 6 possible outcomes, accepted, and 4 flavors of rejection. Invalid call sign, physically impossible, aircraft already existed, conflict advisory. Each rejection fires an instruction result event. The transcript logs the rejection with a reason. The operator hears a negative readback. The aircraft never sees the instruction. The comms input pipeline. Voice or text. Both funnel through the same phraseology parser. Grammar based on ICAO Doc 4444 Chapter 12. Numbers could be digits or spoken. 270 or 270 or literally 270, all pass to the heading 270. Call signs match on phonetic best fit. If you say Speedbird 472 and the sector holds BAW 472, the parser resolves it. Action verbs, turn, climb, descend, maintain, cleared, contact, expedite, map to instruction types. Emergency codes 7500, 7600, 7700, trigger classification events. Declaratives declare hostile, declare unknown, and declare friendlies trigger reclassifications. A bounded ICAO style phraseology grammar for the supported instruction set. Speedbird 108, turn right heading 180.
Right heading 180, Speedbird 108.
Speedbird 108, descend flight level 210.
Flight level 210, Speedbird 108.
So, Whisper transcribes locally, the transcription goes into the parser produces a validated instruction struct, the instruction goes through the comms router, the aircraft's behavior object receives it, crossfades the pilot's TTS voice recording back to clearance in ICAO format, heading first, altitude second, call sign at the end, which is what you just heard. Pilot's readback rendered by Piper TTS locally, or Edge TTS as fallback. Whole loop in under 2 seconds. Voice output uses a local HTTP server bundled as a standalone executable. Piper for primary voices, Edge TTS for the facility voices, Tower, ACC, AWACS, GCI, and the MET. PyInstaller wrapping means that the package build ships without any Python install requirements on the target machine. The reviewer downloads the build, hits play, hears pilot voices with 0 setup. The phraseology reference is a living doc in the repo. Every command the parser understands, with example transmissions. Living reference, not a spec. Anything the parser handles is in there, and anything not in there isn't a supported transmission. The safety layer. 3 concurrent analysis on every tick. Present distance separation between every aircraft pair. Trajectory projection out to 60 seconds. Catch losses of separation before they even happen. Wake turbulence separation using the ICAO Doc 444 matrix. As mentioned earlier, the wake matrix. The light following the heavy, 6 nautical miles, medium following heavy, 5, light following medium, 5, heavy following heavy, 4, 3 miles otherwise. Applied only to trailing aircraft on the same or converging tracks inside a defined wake corridor. Advisory at 8 nautical miles. As they close inside 8, the conflict detector fires an advisory event. Both aircraft's rings glow amber on the scope. The event log gets an advisory entry with both call signs. If they keep closing, the warning at 5 nautical miles, the rings go red, and warning entry in the event log. Under 3, critical, and if the geometry meets the go-around rule, a go-around required event fires. The comms router picks it up, routes it to the aircraft on approach, the aircraft's behaviour object aborts the approach and climbs back to a hold. And there it is, warning tier. Notice the event log format, warning conf 1 and conf 2. Standard tag : description, so the event log's parser color codes it. Every conflict from every tier writes into the same event pipeline. Every one ends up in the after action review at the end of the session. And now, the scoring layer. The session log is a T-array F incident record. Every event to the timestamp, incident type, aircraft involved, details. 10 incident types: successful landing, successful handoff, successful resolution, separation loss, unresolved exit, missed handoff, go around triggered, late instruction, misidentification, violation of restricted zones, aircraft crashed, and airspace bust. Each type has a point value, positive for success and negative for incidents. Running score updates on every event. Efficiency percentage tracked against total incidents versus total handled aircrafts. The difficulty scales dynamically. Spawn interval tightens as the operator's efficiency climbs. It loosens when it drops. It ramps you if you're doing well, and it backs off if you're drowning. The performance tab on the instructor station. The score report is at the top, and then there's 2 columns, operations on one side, incidents on the other. Each row is a category with a count. Every row drills down into a chronological list of every event in that category, time-stamped with the aircrafts involved. That drill down is coming out of rep scoring log, which is a replicated mirror of the local scoring log. Same source in local sim, in network session, and in replay. The spawner. In free play mode, this generates call signs from a pool, picks entry points on a sector ring, samples altitude, speed, and headings from configured ranges. The spawn interval scales with difficulty. The weight categories are weighted towards realistic traffic distribution, mostly medium, with a few heavies and the occasional light aircrafts. Then, scripted scenarios, authored fully in JSON, read from the disk at load time. Every scenario is a sequence of triggers keyed off elapsed seconds or off airspace conditions. Actions cover the full sim surface. Spawn aircraft, set the aircraft heading or altitude or speed, declare hostile or friendly or unknown, activate the jammer, drop the chaff, inject emergency, broadcast facility voice, spawn scramble flights, change the wind, change the active runway, force conflict, force incident. 7 scenarios ship in the current build: Baltic intercept, a distributed sensor fusion showcase with an unknown contact behind a friendly, an operator interrogation, a hostile declaration, a scramble launch, a lead pursuit intercept.
Magic, new contact, east of the sector, in trail of Scandinavian, low altitude, no IFF, closing from behind. Magic, unknown closing on Scandinavian inside 25 miles. Recommend immediate intercept.
Hijack response, a 7500 squawk injection with a 5 aircraft sector already active.
5 aircraft transiting the sector, all squawking standard codes. Maintain standard separation. Speed bird for 72 squawking 7500. Hijack code. Activate doctrine, recommend immediate shadow intercept.
Mass divert, a weather-driven wind flip triggering cascading fuel emergencies.
Weather advisory. Severe storm cell tracking toward the field. Wind shear and crosswind expected to exceed runway limits within 90 seconds.
All traffic, the runway is closed due to severe crosswind. Divert all inbound aircraft to alternate. Repeat, runway closed, divert to alternate. For minutes elapsed. Any aircraft still in the sector is approaching fuel reserve minimums. Expedite divert. Mayday, 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 Speedbird 123, fuel emergency, request immediate landing.
Mayday, 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 Lufthansa 456, fuel emergency, request immediate landing.
Mayday, 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 Air France 789, fuel emergency, request immediate landing.
Mayday, 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 KLM 234, fuel emergency, request immediate landing.
Mayday, 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 RYR 567, fuel emergency, request immediate landing.
Mayday, 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 EZY 890, fuel emergency, request immediate landing.
A Mayday engine fire, a 7700 declaration with priority traffic reroute.
Mayday, 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 Speedbird 394, declaring emergency, request immediate landing. Speedbird 39 for declaring Mayday, engine fire, smoke in cockpit, requesting immediate landing. Clear all traffic from his approach corridor. Speedbird 39 for reports the fire is spreading. For minutes elapsed since declaration. Expedite the approach.
Nordo inbound, a dual traffic 7600 event testing lost comms procedures.
Speedbird 118 squawking 7600. Comms failure. He will fly the published lost comms procedure to the active runway. Lufthansa for 5 also squawking 7600. Second Nordo inbound. Keep the other traffic clear of both tracks.
Cold War probe, a multi-bandit ground control intercept exercise.
Magic, multiple unknown contacts north of the ADIZ line, low altitude, all squawking dark. Stand by for vectors. Magic, 3 unknowns established. 2 believed probes, typical pattern is to turn back at the line. 1 is pressing south on a steady course. Identify and prioritize.
And finally, mixed-ups, a restricted airspace planning problem.
Magic, unknown 02 pressing on civilian Speedbird 501. Recommend immediate intercept.
Active restricted areas published in the sector. 8 civilian transits. Maintain standard separation and route around all P areas. No emergencies expected. 3 minutes elapsed, traffic still working through the sector. Maintain situational awareness on the restricted areas.
Each scenario is checked against the supported doctrine and phraseology rules used in clearance. Every transmission, every emergency response, every intercept geometry, all documented in the test plan. And now the sensor layer. Radar sites are placed actors in the world. Each has a range, an antenna position, a scan interval. The controller iterates every site, every scoring tick, calls paint tracks, and each site fills a tmap fname fradar track of what it can see. Each track carries a truth cosine, a paint confidence, a fade timer, a bearing vector estimate, and an optional secondary return with the aircraft's transponder data. The controller then fuses across every site, latest paint wins keyed on truth cosine, and produces the operator's picture. That's what the operator scope draws. And this is the radar coverage heat map. Every placed site's range disk renders as a soft green radial gradient. Overlapping sites blend additively, and the fused regions read as more saturated greens. The gaps read as absence. This gives the instructor a quick visual read of the radar network coverage, overlap, and the gaps. This is rendered through Slate's custom Vertex API, 48 segment triangle fans per disk, per Vertex alpha. Each site can run one of two detection models. The default is the analytic path, which applies the Skolnick radar range equation to compute a detection probability from transmit power, antenna gains, wavelength, target radar cross-section, and the range. The alternative is the Simulink path from my previous video, where the site synthesizes an IQ cube from live airspace state, runs it through the generated signal processor, and maps CFAR detections back to source aircraft. Both models write into the same fradar struct, so fusion, the operator scope, the EW effects, and the coverage overlays all consume identical data regardless of which model is actually active. Symbology and clearance follows MIL standard 2525 Charlie tactical standard, not a debug sphere or colored dot, NATO affiliation frames, friendly rectangles with rounded corners in cyan, hostile diamonds in red, unknown flowers in amber, neutral squares in green, each with the bearing vector extending from the frame in the aircraft's current direction of motion. The data block anchors to the frame via a leader line. The leader line auto-avoids other data blocks, 18 candidate slots around each symbol. The algorithm picks the least cluttered one every refresh. When two aircraft cluster within 12 pixels of each other, the declutter algorithm fans them out in a small deterministic ring so that the data blocks and symbols stay paired. Real air traffic controller scopes call this data block stagger or symbol declutter. And this is specifically critical for when Chaff paints ghost tracks on aircrafts. The jamming. Speedbird 472 turns on its onboard noise jammer. Under the analytic radar path, its F aircraft state gets a B jamming on flag. Every radar site paints its return at 30% confidence and drops the secondary transponder data. The operator scope shows the primary blip fading, the cosine vanishing off the data block, and only a PRI marker in its place. The operator has to positively re-identify the target before they can issue instructions to it. Under the Simulink DSP path, jamming dims only the jamming aircraft's own return by 30%. Early prototypes tried to null it through the MVDR beamformer, but that took every off-bore site target with it. The behavior I wanted was self-jamming. The jamming aircraft's own return is degraded, and everybody else's is unaffected, which is what real self-protection jamming does anyways. The Chaff. The aircraft dispenses a cloud of reflectors. Every radar site sees a bloom of 5 primary-only returns clustered near the drop point. The F-Chaff cloud struct on the controller tracks the position, the drop time, the fade duration, a total of 12 seconds. Ghost tracks paint at ghost call signs, Chaff 01 through to Chaff 05, with no transponder data. They fade linearly over the lifetime. Under Simulink DSP, the same effect renders as 5 extra IQ contributions per site per CPI, each with a randomized radar cross-section around the drop position. Same track output, and the operator's job is to just keep tracking the real aircraft through the clutter. The instructor sees 2 scopes. Truth scope reads directly off the AirSpaceManager. Every aircraft's real state, real affiliation, real position, no sensor noises, no EW effects. The operator scope reads through rep operator tracks, which is a replicated mirror of the fused radar picture, and this is what the trainee actually sees. In truth mode, jammed aircrafts look identical to non-jammed. However, in operator mode, jammed aircrafts fade, and in truth mode, chaff doesn't exist. In the operator mode, ghost blips clutter the picture. The instructor can watch the trainee's confusion and evaluate their decision making against the ground truth. And one more subtlety: when the instructor reclassifies a contact mid-session, hostile becomes friendly, unknown becomes hostile, it only touches true affiliation and not threat class. The truth scope updates. However, the operator scope doesn't. If the operator hasn't re-identified the contact, they don't get a visual hint that the instructor moved the goalposts. This preserves the training evaluation. And now, the networking. Clearance runs server authoritative. The player is the operator. They own the sector and the aircraft. An instructor can join as a second peer over LAN or via EOS. Instructor peer runs a separate widget, the instructor station, which reads the same replicated data everyone else does, plus a set of server RPCs to inject events into the running sim. 14 inject RPCs. Inject emergency, clear emergency, classify aircraft, scramble fighters, set the wind, spawn aircraft, clear traffic, load scenario, stop scenario, reset scenario, pause the simulation, activate a jammer, drop the chaff, change the timescale, plus scenario control, checkpoint save and load, AAR export, and the federation control. Every instructor action funnels through here. Everyone is authoritative on the server and replicates its effect out to all clients. And, as you've seen throughout the technical breakdown video, 2 play and editor windows, the instructor is on the big screen and the operator is on the small one. Aircraft state, scenario state, the score, notifications, TTS voice, they're all synchronized. The instructor injects an emergency on the instructor window.
Mayday, 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 American 155. Declaring emergency. Request immediate landing.
The operator sees it appear on their scope, hears the Mayday declarations on their radio, sees the countdown timer starting, and watches the aircraft descend under the emergency autopilot script. The instructor panel's main scope. 6 layers rendered in fixed order every frame. Airways drawn first, the underlying navigation grid. Zones next, restricted airspace, MDAs, warning areas drawn as dashed rings with identifier labels. Runways, proper strips sized to actual asphalt length, threshold designators, extended 20 nautical miles dash centerlines. Chaff clouds. Waypoints, named navigation fixes, boundary and heading rows, the outer sector ring with a full 360 degree 12 position compass rows, plus range labels at the cardinal points. Then the aircrafts. Symbols first, then leader lines, then data blocks and a batch pass. The batch pass runs the auto avoid and declutter algorithms across every aircraft at once. And that's why the labels always find a slot, even in dense clusters. Rendered through Unreal Engine's native paint hook on the panel widget. Every draw is a slate line, a slate polyline, or a slate text run. No tessellated materials, no per pixel shaders, and it runs on the widget's paint context, so it composes with UMG Z order. The Performance tab background paints under the scope, the search bar paints over, and there's a master paint gate, so when the Performance tab or the Manual tab is active, neither the scope nor the camera overlay draws, because both draw from the panel root and not from the scope canvas child. Gating child visibility isn't enough. The gate is a C++ bool set by the tab handlers. Next up is the camera view, a live 3D feed of the sector, rendered through a scene capture actor and streamed to the panel's texture. 5 view modes. Firstly, the overview. a top-down mission planning view with drag, pan, and scroll zoom. Next is the tower. Camera locked to the tower position with your pan and tag anchored labels. Next is the chase. This camera is locked behind a selected aircraft, 4 sub-angles, and offsets scaled to the aircraft's mesh bounds. Next, the approach angle. This is a camera per runway, a 3/4 angle. And finally, the operator POV. The actual trainee's first-person view, including their head rotation, replicated live from the operator's pier. The chase view auto-follows the selected aircraft from the scope. Tag anchors so the call sign floats near the aircraft in a world space. Overview is where the instructor plans, drags with the mouse to pan the world, scrolls to zoom in and out, double clicks to resets. The operator POV drops you into the trainee's head. The instructor watches the trainee's actual first-person view. And so every camera mode gets a tactical overlay drawn on top. Runway rectangle outline, dash centerline, threshold designated numbers, 100 nautical miles approach corridor the range takes, 3-degree glide slopes drawn as a 24 segments with a flight level ladder, mil standard 2525 zones as wireframe cylinders with cardinal spokes, sector ring with compass headings, all view gated. Overview hides the corridor and glide slope. Tower and approach and operator hide the runway outline because the operator sees the actual runway through the camera. Per runway active end gating. When wind flips and the active runway changes, the corridor and glide slope swap to the new end automatically. Live, no reload. A pulsing palette, cyan runway markings, magenta corridor and glide, and a golden hour contrast. The sector chart. Waypoints authored as placed actors in the world with named identifiers. Airway segments defined between waypoints. The underlying navigation grid. Restricted zones. Placed actors with a radius and an identifier. Drawn as dash strings labeled with their designators, like R2508, reads like a real IFR chart because it's built from a real IFR chart primitive. The sidebar. The aircraft list. 1 row per active callsign with affiliation icon, phase, altitude, speed. The emergency panel. 1 row per active emergency, sorted by urgency, countdown timer counting down in minutes and seconds, and red under 1 minute, amber under 3. The event log. Every conflict, every crash, every intercept result, every airspace bust, every notification the operator saw. The ring buffer, capped at 40 entries, so old events just scroll off. All 3 widgets use a prefix diff populate path, a key matched walk that only rebuilds the diverged suffix of the list. No clear children on every refresh, no flash, persistent widget instances across updates. Necessary for the event log, which updates every notification, and for the aircraft list, which updates every scoring tick. The comms transcript. Every radio transmission, every instructor inject, every system event, color-coded by role, 10 roles, operator, pilot, system, instructor, tower, ACC, AWACS, GCI, ATIS, and MET. Each role has its own palette, so the log reads at a glance. Pilot readbacks are rendered in ICAO Doc 4444 Chapter 12 strict format. Target value first, no action verb, call sign at the end. Heading 270, flight level 217, Speedbird 472, not Speedbird 472, roger, turning left into heading 270. Real ATC readback conventions. Filter drop-down at the bottom, multi-select, show only pilot transmissions, or only instructor injects, or only conflicts and system events. Useful during AAR walkthrough when you want to focus on one thread. And as you've seen throughout the video, the instructor inject control section. You right click any aircraft row and you declare an emergency. You have fuel low, general mayday, hijack, NORDO. Each fires the appropriate voice line, the appropriate transponder squawk, and the appropriate autopilot script. Then you have the sector-wide controls at the bottom row. The wind bearing and speed sliders. Dial them, and the active runway auto swaps. The max aircraft slider, how many aircrafts the sector allows concurrent. The timescale slider, pause, quarter speed, half, 1, 2, 4 for reviewing incidents, or speeding through the quiet stretches. Pause, reset scenario, clear traffic. Then, the in-station reference wiki. 10 sections covering the whole operator surface, the overview, the session lifecycle, the truth scope, the camera view, the injects, the scenarios, the checkpoints, the performance in AAR, the federation, and the button reference. A sticky table of contents on the left with anchor jump, and a search bar at the top. Every button reference is color coded to match its actual UI color. Jam off is green, pause is yellow, and scramble is red. The content is authored server-side in C++, hard-coded strings with lightweight markup, so the manual ships with the binary, no data dependency, and no missing content on the package builds. The session replay, server authoritative. Every scoring tick, the recorder captures a snapshot of the airspace state, every aircraft, every wind, every scoring counter, the transcript log, and the notification ring. Snapshots go into a ring buffer keyed by timestamp. The bottom of the panel scrub bar. Enter replay hits the recorder, pauses the live simulation, poses the world to the snapshot of the scrub position, drag the slider, and the world scrubs with it. Every aircraft, every conflict marker, every operator advisory, every transcript entry, synchronized. Segment seams are painted as tick marks on the bar. Every time the operator resumed live from a replay, that boundary shows. Speed control at quarter, half, 1, 2, 4 for reviewing incidents at slow speed or skimming across quiet stretches. Go live, and it returns to real time and unpauses. The buffer keeps accumulating across replay cycles, so you can review earlier and later events in the same session. Then, you have the session checkpoints. The multi-attempt training workflow that every defense courseware ships. Instructor sets up a complex scenario, 5 aircraft, active emergencies, active conflicts, hits save checkpoint with a name. And all the trainees state, every aircraft, every wind, every score counter, every incident in the log is captured as one snapshot. First, the trainee attempts it, and when they're done, or when they've failed, the instructor hits load checkpoint. Sector wipes back to the state it was in at save. Second trainee attempts the same scenario, same aircraft, same initial conditions, rinse and repeat. Fully replicated so that the joining instructor peer sees the same checkpoint list. Transcript isn't cleared on load, keeps the full attempt history for the AR. The after action report. One button, server authoritative, writes a full session report to the disk as a markdown. A header with timestamp, session duration, scenario, win conditions. A summary block, total handled efficiency percentage, successful handoffs, incidents, resolutions, intercepts, emergencies. A chronological timeline of every scoring event with aircraft and timestamps. Critical incidents drilled down auto-selects the catastrophic events like misidentification, restricted zone violation, crash, separation loss, and includes the 60 seconds of comms leading up to each. A full transcript at the bottom with role tagging. Runs through Git if the operator wants the version training runs. Portable, reviewable, and this gives the instructor a portable record for review, comparison, and after action discussion. Then, the verification. 52 automation tests across 7 domains, covering 69 requirement IDs. Every test is an implement simple automation test case, runnable from the editor's session front end. 7 domains covered: DIS, wire format, entity state PDU, fire, detonation, emission, signal, transmitter, a round trip and malformed rejection, FED, Federation layer coverage across DDS, RTI Connect and HLA, comms, instruction validation and phraseology, envelope, military bypass, non-finite rejection, safety, ICAO Doc 4444 wake matrix, RVSM vertical minima, horizontal separation thresholds. Score, session lifecycle, difficulty ramp, SIM, session recorder, start-stop, duration, poseback, events in range, and radar, Simulink DSP wrapper harness. 69 requirement IDs tabulated in the requirements doc. Every test's leading comment tags the rec ID it covers. Full traceability from requirement to test. The V&V plan documents the TIS. Automation is the unit tier here. Manual procedures cover the runtime dependent checks. Wireshark for DIS, RTI admin console for RTI, HLA subscriber for Federation join, and 2 Federate live test, and the full automation pass. This is the kind of traceability discipline I wanted the project to demonstrate. A single command, 52 cases, and all pass. Then, the Network Federation covered end-to-end in the interoperability video. 4 transports currently supported: DIS, DDS, RTI Connect, and HLA, sharing the same integration seam. The DIS emitter subscribes to on-aircraft state updated. Every state commit becomes an entity state PDU on the wire in RPR format. Every incoming PDU from a federated peer flows in through the same registration path as a local spawn. DDS, RTI, and HLA follow the same pattern on their respective buses. Same subscriber, different marshaller. All 4 are toggleable live from the instructor panel: host, port, start, stop, and the packet rate indicators. Because state changes flow through delegates, every federation layer is a pure subscriber, no parallel plumbing per transport. The selected federation layer publishes the same authoritative simulation state the local systems consume. Wharton, a public geospatial reconstruction of the airfield at AGNO using cesium tiles and place runway geometry. 53.7 north, 3 degrees west. Photogrammetry via cesium for Unreal. Google photorealistic 3D tiles, plus OSM buildings, real terrain, real airport layout, real approach paths, all sourced from public geospatial data. Physical runway placed as a blueprint actor with the actual asphalt dimensions: 2200 meters long, 45 wide. Designator override forces the ICAO number so that the label reads what the real signs say. Approach corridor lines up with the real approach. And then the operator VR pawn in a diegetic tower interior. A video for this will be released soon. The scope renders on a physical monitor mesh in world space. Emergency panel on a second monitor beside it. Then mimic panel controls. Physical buttons on the desk for push to talk, call sign selection, emergency acknowledgement, and runway change. This mirrors the physical layout of a live ATC operator station. The trainee stands in the tower, presses physical buttons, reads scopes on physical screens, talks over a physical microphone. Everything the sim renders is diegetic. The VR performance profile is documented: lumen off, TSR off, TAA on, substrate on for the sky, dynamic pixel density, LOD forcing, streaming pool size for cesium, holds 72 Hz on a Quest 3 over Link. And that is clearance. C++ engine underneath every layer, single source of truth for aircraft's state, single movement executor per aircraft, a read-only safety analysis, validate before execute on every instruction, a controller-driven tick order, strict presentation boundary, and everything mentioned. The sensor fusion, the electronic warfare, the 7 scenarios, the multi-role transcript, the replay and checkpoint workflow, the AAR export, the DIS and DDS and RTI and HLA federation, the Simulink autopilot and radar signal processor, the VR operator station on Wharton. Everyone is a subscriber to the same event-driven core, and that is the story. One thing to say plainly is that Clearance is still a portfolio demonstrator and not an operationally validated training product. The value here is the architecture, the integration pattern, the verification discipline, and the training system workflow. The repos and design docs will be linked below as soon as they're public.